In this video, we will use the ideas of impulse and momentum to solve the following problem. A pitcher in a baseball game can accelerate a baseball with a mass of 145 grams from rest to 95.5 miles per hour. We will consider the force the pitcher exerts on the ball to be a constant 52.4 newtons and neglect any ball the spin may have. We're asked the following questions. What is the change in the baseball's momentum during the pitch? How long is the baseball in the pitcher's hand? What acceleration does the pitcher produce? And finally, assuming the ball moves perfectly horizontally, what distance does the ball move before the pitcher releases it? Well, the first step in the problem-solving process is always to read the problem carefully and figure out what the problem is trying to tell you. Then write that data down, making sure that it's all in the appropriate units. So we look here at the problem, and we can see that we're given 4 pieces of data. First, we are told the mass of the baseball. We're told that it starts from rest and ends at 95.5 miles per hour, and that the force is a constant 52.4 newtons. And so we can go now to write that out. The mass of the baseball is 145 grams. Now that's not the proper units, but we can use the conversion factor that 1 kilogram equals 1,000 grams to turn this into 0.145 kilograms. Next, we're told that the initial velocity of the baseball is 0 because it starts from rest, that the final velocity is 95.5 miles per hour. That is also in the wrong units. We need it to be in meters per second. So we use the fact that there are 1,609 meters in 1 mile, and 1 hour has 3,600 seconds. And that gives us the result that the final velocity of the ball is 42.68 meters per second. And finally, we are told that the constant force exerted on the baseball is 52.4 newtons. So we've now written out all of our data, and we've made sure that everything is in the proper units. The next step is to read the problem again and figure out what the problem is asking us for. For at least the first part of the problem, we are asked what is the change in momentum for the baseball, delta P. And we know that means that the mass times the final velocity minus the mass times the initial velocity is the change in momentum. So that's step 3, finding a way to connect what you know with what you are expected to find. Well, now that we have this in hand, it's easy to simply plug in the numbers and figure out that the change in momentum is the mass of the baseball times the baseball's final velocity minus the mass of the baseball times the initial velocity of 0. This gives us a change in momentum of 6.189 kilogram meters per second. Notice the unusual units on momentum. Also notice we are keeping an extra figure here. This problem has 3 significant figures, but we're keeping this extra figure for future calculations. We would report this as a change in momentum of 6.19 kilogram meters per second. Next, we are asked for the time that the ball is in the pitcher's hand. For this, we can consult the impulse formula, which says that the impulse is the change in momentum. In other words, force times time equals delta P. We've already figured out delta P, and we are told the force. So plugging in those figures, we get this, and then we can solve for the time, 0.118 seconds. We worked a problem exactly like this one back when we were talking about the work energy theorem. And ultimately, this is the time that we got, utilizing the work energy theorem to find out how long the ball's in the pitcher's hand. So we have reproduced that result, which is always encouraging. We're then asked, what acceleration does the pitcher produce? There are actually a couple of ways to get this. We could simply use the definition of acceleration, since we know the final velocity, 42.68, and the initial velocity, 0, and then the time in the pitcher's hand, 0.118 seconds. That gives us an acceleration of 361.4 meters per second squared. We would report that as 361 meters per second squared. However, there's another way to do this. We could also utilize Newton's second law. Since we know the force applied and we know the mass, we can just take the force divided by the mass, 52.4 divided by 0.145, and that also gives us an acceleration of 361.4 meters per second squared. It's always good to have a couple of different ways to calculate something, right? And notice that this second method does not rely upon us to have calculated the time correctly. This is actually a good check to reassure ourselves that we did it correctly. Finally, we are asked, assuming the ball moves perfectly horizontally, what distance does the ball move before the pitcher releases it? Right? Well, we can rely upon one of the kinematics formulas for this. Final velocity squared equals initial velocity squared plus 2 times acceleration times the displacement. With a final velocity of 42.68, an initial velocity of 0, and an acceleration of 361.4 meters per second, we can calculate the acceleration times 2 is 722.7, and this allows us to calculate the displacement, 1821.6 divided by 722.7. That gives us 2.52 meters. So the ball experiences a displacement of 2.52 meters while it is in the pitcher's hand. Again, this is the same result that we got when we used the work energy theorem. So this is an encouraging result. Not terribly surprising, since both the impulse formula and the work energy theorem are derived from Newton's second law.